Today we discuss polymer material selection for electronic applications. Okay, let us get started. Today we have three different sections, so we start with the material selection, criteria for electronic applications, then we discuss some component characteristics, and then we jump into selected materials. I have some commodity materials, some engineering polymers, and some high performance polymers. Okay, the material selection criteria. So for electronic application, one of the most important criteria is weld thicknesses. So they are most of the time less than 1 millimeter. So the polymer must have good melt flow during the molding process and without sacrifice in any more performance attributes. Then we have mechanical strength and service life. So you have to imagine when you have now thin wall thicknesses of less than 1 millimeter, so the product itself needs to have then also the necessary mechanical strength to fulfill the design purpose and also over the whole service life. So we talk here typically can be fibers up to 20 years. Then also another important criteria is that dimensional stability. So we have the ensure to that the selected materials has a shrinkage and warpage in a minimal range, so we have typically tolerances below 5 micrometers, and also is particularly important for printed circuit boards or PCB materials, which need to be really flat to mount the different sensors on it. The another aspect is flame resistance. So need to be short for UL94 V0 level, also with the use of halogen free flame retardants where possible. Then we have high thermal stability, so we already mentioned it. Reflow soldering process is for the printed circuit boards we have here. Temperature peaks 270 degrees Celsius, so here to be resistant to any chemicals which may splash or immerse with the component itself. So this can be hydraulic or its cleaning agents and also all kind of lubricants. Furthermore, it can also be that we have some sliding components involved in the electrical device. So if it's the case, this should be as less as possible dust production and to keep a good tribological qualities. Then of course electrical performance of the materials. So they're depending on the part and the application, the resistivity and tracking performance is needed. And also humidity is a part of some polymers are subject to hydrolytic degradation, and this can then in the long run lead to part failure. So this needs to be kept also in the back of our minds. Okay, now let's discuss some component characteristics. So when you look at the electrical components and in particular enclosures, there is called increased protection numbers. So the IP number. So it's used to express the protection against the increase of foreign bodies of water and depending also on the IP rating. The several other things are affected, for example, the method of fixing use, the method, the method of sealing, and also the when you have the cable entrance into the device, and sometimes so you have always two digits, but sometimes there also the effort digit added to express the impact protection. So let's have a look. For example, here is a table of the different IP levels. So in particular, the first digit, and then here we have the second digit table. So let me take now example IP protection 66 means when we go here now in the table 1 on the 6, that means we need total protection against contact and increase of dust, and the second 6 is 10 air protection against high pressure water trace from any direction. So this is a typical IP scenario. So and this You have to consider them for the material selection to always check such tables. Such Okay, let's continue with the selected materials. We start with the commodities, and here I've selected polypropylene because it's a well-known low-cost material. We have here well-balanced relationship between toughness, stiffness, and hardness. And also we have some heat resistance up to 100 degrees Celsius. We have excellent resistance towards chemicals, low water absorption, and also low permeability to water vapor. It's easy and flexible in processing, so it doesn't matter if you want to mold or extrude. And although we have a low density, and this result in applications so that we have a variety of electrical and electronic applications. So here are named for examples: the battery containers, cable retention clips, screws, nuts, and washers for examples. Okay, let's continue with the engineering polymers, starting with ABS. So here we have also good dimensions, stability at both high and low temperatures. ABS can be coated with metallic, for example, Nikki. We have the Dowell 94 classification from ranging from HP to V0, and also excellent impact behavior. And so a case use example is the in, in intricate parts of, for example. Then we continue with polyamide or PE. So it is selected for electrical and components because of the good chemical, electrical, and mechanical properties of the material, combined with flexibility and relative immunity to fracture. So we have also a UUL 94V0 with the use of frame retardants, and we can also withstand temperature up to 200 degrees Celsius with the heat stabilization applications. Also a large field ranging from memory connectors in input-output conductors connector support via wired wire connectors. So connectors in general, also modular check micro switches. Then we have PPT. PPT is also used because of the high dimensional stability, good surface finish, and good electrical and mechanical properties. And we have no dioxins or for forming substances. Also, UL94 flammability classification from V2 to V0 is possible, and it is used in housing connectors, microconnectors when you use high flow PPT. And also enclosure, here again comes the RIP rating into the game. And then I have also selected polycarbonate or PC. The amorphous engineering polymer here, this is a rigid and dimensional stable material as high impact resistant over a wide temperature range, also good resistance to chemicals, and has the advantage of transparency and good insulation properties. And when you look at the applications, air enclosure of the category 5 and 6 tend to be most of the time polycarbonate. Let's continue with the high performance polymers. To start with, polysulfone amorphous high performance polymer, which is tough, rigid, and has a high strength with a high heat deflection temperature. It has also a good dimensional stability with constant electrical and mechanical properties over the right temperature range. Then we have an excellent surface quality of polysulfone, which enable that it can be metallized in a direct way. As applications, we have ranging from enclosures, sensors, bobbins, solenoids, connectors, and fuse boxes. Then we have polyphenol sulfide or PPS. It's a semi-crystalline high-performance polymer, also especially known for its high heat performance together with the high heat, high deflection temperatures. The range of 260 degrees Celsius. We have exceptional processability With injection molding, that means we have an outstanding dimension stability, in particular in injection molding. When high precision molding is needed with to fulfill severe tolerances, with a high chemical resistance and replacement of high performance thermosets or metals is possible, and for application BPS can be used for surface mounted connectors where we need this high heat diffraction temperature, and also replacing conventional materials in applications such as housing of mobile phones or other information devices. Then we have liquid crystal polymers or LCP. There we have the special molecular structure, so you have to imagine you have rigid root-like macromodules which align in a melt, and so you have in liquid structures which have a self-reinforcing effect. You can imagine similar like glass fibers. It has extremely good flow properties, and this allows you to mold really thin walls of modern connectors. We have also continuous server temperatures up to 240 degrees, short term even to 240 degrees Celsius, and there is no problem to use it in the soldering process. And this you can send applications, so it's used for connectors, thin wall connectors, printed circuit boards, everywhere where you have the reflow soldering process. Okay, let's move on to material selection for natural fiber composites. A composite material is a combination of two materials with different chemical and physical properties. When these materials are combined, they create a better material, one that is an improvement on the base material's individual properties and can be applied in more situations. By creating this composite material, the resulting material may be stronger or lighter. Perhaps it has been made more durable or has better electrical conductivity. A specific type of composite known as fiber reinforced polymer composites are high performance materials made from a matrix which has been reinforced with an engineered man-made or natural fiber, such as glass, carbon, or aramid. In a fiber composite, the matrix protects the fibers from damage and transfers the load between the fibers. The fiber in turn provides strength and stiffness to reinforce the matrix and resist cracks and fractures. Natural fiber composite is a subset of fiber reinforced composites, where the reinforcing fibers are or both the resin and fibers are derived from renewable or natural resources such as wood or plants. The concept of composite materials dates back to 3400 BC, when the Mesopotamia glued wood strips together at different angles, creating the first plywood. Today, composite materials make up much of the world around us. Maybe you've installed fiberglass insulation, experienced the swing of a carbon fiber golf club, or launched in the sun on a wood composite deck. These remarkable materials have been designed and tuned to withstand our most demanding app applications. But next is material selection for components, concurrent engineering perspective. An important class of material is composite materials. By composite material, we mean a man-made multi-phase material. We have met multi-phase material previously like steel, in which ferrite and cementite is there, but that we will consider because ferrite and cementite both phases from during natural cooling of a steel from the austenite phase. So that by man-made we mean that the two phases were individually existing and then they were put together to form this composite material out of two places. One is generally a continuous phase which is called matrix, and another is discontinuous phase which is called reinforcement. Although in some composites like sandwich composite, both phases may be discontinuous. Now, composites can be classified on the basis of the nature of matrix. So we have polymer matrix composite, metal matrix composite, and ceramic matrix composite. Depending on whether the matrix is polymer or metal or ceramic. Example of polymer matrix composite will be JFRP, which is short for glass fiber reinforced. So in this, in a plastic, for example, polypropylene or epoxy glass fibers are both. So that is glass and for reinforcement. So glass fiber reinforced plastic, or we have CFRP, carbon fiber reinforced plastic. Many times in sports equipment like racket and all are sold as carbon racket. They are actually carbon fiber reinforced plastic. Similarly, many commercial products are known to be made of fiberglasses, but fiberglass is actually glass fiber reinforced plastic. Then you have metal matrix composite. An example of a metal matrix composite, one can take aluminum as the matrix and reinforce it with its own oxide L2O3. So L2O2 is the alumina is reinforcement, and aluminum is the matrix. Ceramic matrix composite in the matrix will be ceramic. So let us take ceramic Al2O3. Alumina is as the matrix. This can be reinforced with silicon carbide fibers. So silicon carbide fibers can be used as a reinforcement for alumina ceramic. So it is a ceramic matrix composite. Here I show you a classification scheme of composite based on a shape and and distribution of reinforcing phase. So the reinforcing phase can be particle. So we will say a particle or particulate composite, or can be a fiber. We will call it a fiber composite. The reinforcing fiber can be either be discontinuous or short fibers, or it can be continuous and long fibers, which are aligned. The discontinuous short fiber can also be aligned or could be random. So depending on the orientation and shape of the reinforcement, we can classify the composite into different classes as shown here.
Good evening, everyone. I am here to tackle about design considerations. So, firstly, what is design consideration? Design consideration are areas that may affect the requirements, design, or operational concept of a system and should be part of the system engineering process throughout the acquisition life cycle. Some design considerations are concepts that assist system engineering trade-offs and ought to be accommodated or applied to each system, program, or project. Others are constraint, boundaries, or limitations, with values that can sometimes be tailored or negotiated, but which in general represent fairly immovable parts of the trade space. Many design considerations are mandated by laws, regulations, or treaties, while others are mandated by the domain or service component. These mandates should be incorporated during the requirements analysis process to achieve balance across all of the system requirements.
About design consideration in electronics, the design consideration are formulated to bring to the attention of the designers in applying universal accessibility design principles and requirements to building and facilities. They can also be used to identify barriers in existing buildings. Design consideration in electronics engineering involve the selection of components, circuit design, and system integration. Factors such as cost, power consumption, reliability, and manufacturability must be taken into account when designing electronic systems. And it also includes circuit board layout, power regulation and noise reduction, temperature control, and component selection. Additionally, designers must consider material compatibility, electromagnetic interference, dissipation, reliability, durability in order to create a successful product. And the most important in design consideration include material choice, shape and form consideration, aesthetic concerns, functional criteria, safety requirements, cost consideration, environmental sustainability, circuit board layout, power regulation, and noise reduction. All of these elements must be taken into account when designing an effective and impactful product. Example of design consideration include material choice for structural integrity and durability, shape and form consideration for aesthetics, ergonomics, and functionality, aesthetic concerns for visual appeal, functional criteria for usability and operational performance, safety requirements to safety requirements to protect users, cost consideration to stay within the budget, environmental sustainability for eco-friendliness, circuit board layout for efficient power consumption, and power regulation to manage voltage and current levels, and noise reduction to reduce interference.